Hi, and welcome to the final video on projectile motion. One of the things that people often ask about is how fast is something going at a given point in the arc. Now, we can do this many different ways, but the most common way to do this is if we know the x velocity and the y velocity, we can put those two together and find the total velocity. This is easiest at the top, at the peak, where there is no y velocity, it's just x. But at any given point, say here, you'll have an x component and a y component, and the two of those together will give you a velocity in the direction of the projectile. Now, for general parts of the flight, this isn't particularly useful or meaningful. What we typically care about are three locations. Number one, the launch. Number two, the apex. And number three, the impact. Because everywhere else in the flight, finding the total velocity doesn't mean much, especially at this level. So what we do is we talk about those. Let's start with the original launch line. The original launch is the easiest. We've been using it all along. Once we know what the velocity is in one direction, we can find it in the others. The velocity at the top, at the peak, at the apex, is only the x velocity. There is no y velocity. At the apex, Vx equals V because Vy equals 0. The final point we typically care about, and the only one we haven't talked about thus far, is at the moment of impact. At the moment of impact, let's take this little section here and blow it up. So whatever your object is, be it a tennis ball, football, cannonball, or cars, careening off cliffs is a common thing, it's going to come into the ground and strike with a velocity. Now, this impact velocity tells us things down the road, so we need to discuss how we get there. From a kinematics point of view, it's the same thing we've been doing. Your Vy and your Vx. Your Vx will be the same Vx that you had here, the same Vx you had here, because that's not changing. Your Vy you'll actually have to calculate. Once you've calculated, however, you have a right triangle. You can find both the velocity and the angle of impact, or the angle it makes when it collides with the ground. Both these can be useful information, particularly if you want to start from this point of information and work backwards. A computer program that I worked on while I was at ISU was taking the angle and velocity of impact and working backwards to figure out how high up a car would careen off a cliff at, telling you where on, say, a mountain road it came off of, and the such. This information would also tell you how fast they were going before they went off the cliff, thus allowing you to determine if it was sabotage, if it was manufactured, if they were doing the speed limit, what exactly was going on, what was the cause of death. So this information can be useful one way or the other. What we're going to focus on right now is how to calculate that velocity and how to work backward from that velocity. So we've done this problem before. Car goes careening off a cliff. If it's traveling at 60 miles per hour, which is about 27 meters per second when it goes off the cliff, how far from the cliff does it land? We've done that problem. So what we're going to do today is change it up. I still want to know how far from the cliff does it land. But I also want to know how fast it's going when it lands. Now, when I say how fast it's going, I don't mean its x or y components. I mean those combined. I want to know v, not vx, not vy, v. And since I'm asking anyways, I want to know the angle of impact. Now, this seems hard and messy, but we've already done these problems before. It's not hard. We talked about how the x values. Delta x is an unknown. Your v initial x will equal your v final x, which will equal whatever you get from this triangle. You know that your acceleration in the x direction is 0. You don't know what t is, but we'll get there. In the y direction, we know our delta y, it's the height of the cliff. We know the acceleration in the y direction is going to be negative 9.8 because of gravity. It's falling through the air. We can even find the initial velocity from, again, breaking up this triangle. What we don't know is the velocity and time it hits the ground at. And to solve this problem, you need to find both. So let's go through this as per normal. First things first, let's break up this triangle. Sine 15 equals the initial y over 27, which means v initial y equals 27 times the sine of 15 degrees. Do the same thing for x. Cosine 15 equals v initial x over 27, which means v initial x is 27 times the cosine of 15 degrees. Go ahead, take those, plug that in your calculator. Now that we have our acceleration, our delta y, and our v naught, we can find v and t. Now, because we're solving for both v and t, we can do it in either order. We know that solving for t will require a quadratic, so why don't we solve for v first? The equation that has v, delta y, ay, and v initial is this one. And since we're solving for v, all we need to do is take the square root of the right side. Making sure you plug in all your values, not just some of them. When you solve for Vy at the moment of impact, or the instant before it hits the ground, because it's still going to be moving right up until it hits the ground and even slightly after. You should get, it's going 46.96 meters per second. I say 46.96, but that's a positive or negative. Do I take the positive or negative answer? Well, think about it logically. Up is positive, down is negative. The car goes up, and then it starts going down. So the answer we want here is the negative, not the positive one, because that matches what we see and what we think about. Do be careful with such things. Now, now that I have this, I can go ahead and solve and talk about the v of impact and the angle of impact right now. Because I know the final velocity for y, the moment of impact, and I also know the final velocity for the x, this 26.08, because it doesn't change. So right now I can just draw a triangle and zoom in on how fast this car is going right when it impacts. The Vy going down is negative 46.96 from right here. And the Vx is the 26.08 that I talked about earlier. So from here, I have a right triangle, and the total velocity, or the v at the end, is going to be this side. And the angle of impact right here, well, we can find that via tangent. So what I want you to do right now is go ahead, find v that I've set up for you, find the angle of impact above or below the horizontal, and while you're at it, tell me how far away I am. Finish out solving for t, plug it back in up here. So the answers you want are in the top right corner for quick check. Delta x, or the distance from the edge of the wall, is 143.57 meters. The velocity it impacts is at 53.72 meters per second. The angle it impacts is 60.95 degrees above the horizontal. Now let's talk about how I got there. The v and the angle are really easy. I did exactly what I said, Pythagorean theorem here. Notice how the negative's inside the parentheses to give me a positive number, and I did a tangent. You'll notice I left the negative out. Had you left that in, you would have gotten this angle here, and then you would have to think back and go through it. It would get you the answer either way. I use reference angles as a way to cheat and make my life easier, and just tie it back to the drawing. Either way will work. The slightly harder one is the delta x, but we've done this problem a couple times. Using this values here, you can go through and solve, but you'll notice I didn't do the quadratic because everyone hates the quadratic. Since I already had v, I could use any equation I want. This one is the easiest one that'll give me t. It doesn't involve any squaring or annoying calculations. It's just right there. So I can rearrange it, plug in my numbers, get 5.51. Once I get that 5.51, I can plug it in over here. Again, since this is 0, it just falls away. Give me the 143.57. Awesome, easy peasy. Okay, let's talk about how we'd work this one backwards. I'm going to set you up, but you're going to try that one on your own. In mountainous regions, there are several road points next to a cliff or mountain that if a car careened off, they'd all end up in the same general valley. One of the cases where I wrote a computer program for to solve one of these scenarios is based on the angle of impact of a car and how crumpled it is, you can tell how fast it was going when it hit. So in this case, the car hit the ground going about 42.3 meters per second, an angle of 52.1 degrees. Based on this information, the officers investigating this would like to know how high up the mountain road it was when it careened off so they can narrow the search and look for other evidence. Using the information on the screen and assuming that it's driving straight off the cliff, how high up the cliff or mountain was this car when it careened off? Go ahead and give it a try. Check back. Okay, let's take this one from the top. The first thing I did was break down the impact angle and velocity into components, one for x, one for y, and then you set them up using the x and y equations. I solved for the t of x, but once I found all my givens, I realized I didn't actually need to. I have the v naught y because it's a flat surface, and I have the v final y from over here, and the acceleration in the y direction. I could find t directly from y, or I can find delta y from y. Right off the bat, don't even need the t at all. I found the t just for good measure to show that you can and how you could work that backwards from there. But ultimately, I just used the v naught y, vy, and ay to find this equation to find your delta y. Plug in your values, you'll get negative 56.85, which means it went down 56.85 meters, which means the cliff that it fell off of, in this case, was 56.85 meters tall. If there had been an initial velocity in the y direction, say it went off a ramp, we would have to solve it
using the t value.
It would be potentially a question is we don't know the angle it came off the cliff at, so we don't know if it had an initial y velocity. Find out how tall it is, at which point you would not be able to solve it, and you'd need to go through the time, like I did here. But in this particular case, because v naught y was 0, we didn't need to do that work. Okay, thanks for watching. Have a good one.